Here are two numbers, 67 and 73. They are two measurements of the same thing. How fast the universe is expanding right now, made by two teams using the finest instruments our species has ever built. They are supposed to be the same number. They are not. And here is the part that should stop you. As the measurements got sharper, the two numbers did not move closer together. They drifted further apart. The Big Bang is the most successful theory in the history of science. It predicts the temperature of the infant universe to better than 1 part in 1,000. And yet, the closer we look at it, the more it refuses to agree with itself about its own expansion, about what 95% of it is made of, about the very moment it began. So, what is actually going on? Why does the best theory we have make less sense the more carefully we study it? Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will understand exactly what it means when a theory this good starts to come apart at the edges, and why that might be the most hopeful thing happening in physics. Now, let's slowly ease into this part 1, the most successful theory we have. Let me begin by telling you something that will make everything else in this video stranger, and it is this. The theory we are about to slowly take apart. The theory that seems to fall further out of focus every time we look at it more closely is not a bad theory. It is not a shaky theory. It is by almost any measure you could name the single most successful description of the universe that human beings have ever written down. So before we go anywhere near the cracks, I want you to feel how solid the ground is, because the whole strangeness of tonight depends on it. The idea is simple enough to say in one breath. The universe was once hot and dense and much smaller than it is now. And for something like 13.8 billion years, it has been expanding and cooling into the vast, cold, quiet thing we live inside tonight. That is the Big Bang. Not an explosion, not a bang, not really, though we will come back to that. Just a universe that used to be small and hot, and has been growing and cooling ever since. And from that one idea, physicists built a model. They gave it a slightly clumsy name, lambda CDM, which stands for a cosmological constant plus cold dark matter. And we will meet both of those characters later, because both of them are trouble. But here is the thing about this model that you need to hold on to. It runs on only 6 numbers, 6. You feed in 6 values, 6 parameters measured from the sky. And out of those 6 numbers, the model reproduces an astonishing sweep of everything we see. It predicts how fast the universe is expanding. It predicts the exact recipe of the lightest chemical elements, how much hydrogen, how much helium, how much of a trace of lithium was cooked in the first few minutes of time before there were any stars to cook anything. And most impressive of all, it predicts the faint pattern of warmth and coolness printed across the oldest light in the sky, the light we call the cosmic microwave background. And it matches that pattern to a precision better than 1 part in 1,000. Think about what that means for a moment. A theory built from 6 numbers tells you what the temperature of the entire sky should look like when the universe was less than 400,000 years old. And then you point a satellite at the sky, and the sky agrees decimal place after decimal place. That is not luck. That is not hand-waving. That is one of the great intellectual achievements of our species. And no serious scientist anywhere doubts the core of it. The universe really was hot and dense. It really has been expanding. This is as settled as the fact that the Earth goes around the sun. Let me give you just a little more of the recipe. So, the size of the achievement really lands. In the first few minutes after the beginning, when the whole universe was hotter than the center of a star, the lightest atomic nuclei were forged. The model predicts that this early cooking should have left the universe about 3/4 hydrogen and about 1/4 helium by mass, with just a faint trace of a couple of other light elements mixed in. And when we go out and measure the oldest, most pristine gas we can find, gas that has never been through a star, that is almost exactly what we see. 3 parts hydrogen to 1 part helium, matched to within a percent or two. The theory reached back to the first 3 minutes of time, told us what elements should exist, and the universe agreed. And the microwave background does something even more remarkable than simply matching. Its pattern of warm and cool spots has a series of peaks, a kind of cosmic sheet music, and the exact heights of those peaks encode how much ordinary matter and how much dark matter the early universe contained. Physicists predicted the shape of those peaks before the best measurements came in, And when the measurements arrived, the peaks stood exactly where the theory said they would. The third peak in particular is a direct fingerprint of dark matter printed into light that is nearly 14 billion years old. When a theory predicts something that specific, that far in advance, and the universe delivers it, you have earned the right to trust that theory deeply. This is not a house of cards. This is a cathedral. And that is exactly why the cracks when we find them are so unsettling. You do not worry about cracks in a shack. You worry about cracks in a cathedral. So keep that feeling close. The feeling of standing on something firm because I am about to start tilting the floor. Here is the quiet paradox that this whole video lives inside. Over the last 15 years or so, and with a particular sharpness since around 2019, something odd has been happening to this beautiful, successful theory. As our instruments got better, as our telescopes got larger, and our surveys got deeper, and our measurements got more precise, the theory did not get more comfortable. It got less comfortable. The numbers started to disagree with each other. Not wildly, not everywhere, but in specific, stubborn, sharpening ways that refused to go away. The most basic quantity in all of cosmology, the rate at which the universe is expanding right now, has split into two different answers depending on how you measure it. And the gap between those two answers has grown into what physicists now openly call a crisis. 95% of everything the universe contains has turned out to be two substances that nobody has ever directly detected, that we know about only because we can feel their gravity. And just in the last couple of years, the largest map of the cosmos ever made has begun whispering that one of those substances, the one we assumed was a fixed and unchanging feature of empty space, might actually be changing over time. That is the paradox. The Big Bang works better than almost any theory ever devised by anyone. And the closer we look at it, the less internally consistent it becomes. The better our eyes, the stranger the picture. And tonight, we are going to walk through that strangeness, slowly and carefully, one crack at a time, until we understand what it might actually mean. Because the answer, when we get to it, is not what most people assume. It is stranger and quieter, and in a way more hopeful than either the people who say the Big Bang is a lie, or the people who say it is finished and perfect. So settle in with me. We are going to start not with a crack, but with the deepest one of all, the one hiding at the very beginning, at the moment the theory is actually named after. Because it turns out the Big Bang has a problem right at the instant of the Big Bang, and it is a problem the theory can never solve on its own. Part 2. The one frame the film cannot show. I want you to imagine that the entire history of the universe is a film, and we are going to run it backward. Right now the film shows what we see tonight. Galaxies scattered across the dark, drifting apart from one another. The whole thing slowly expanding, slowly cooling. Now we start to rewind. As we do, the galaxies begin sliding back toward each other. The space between them shrinks. The universe grows smaller. And because you cannot squeeze a universe without heating it, it also grows hotter. Keep rewinding. The galaxies dissolve back into formless glowing gas. The gas grows denser and brighter until the whole cosmos is a single, uniform white glare, hotter than the core of any star. A fog of pure radiation so thick that light itself cannot travel through it. Keep winding the film back. The seconds compress. We pass the moment when the first atomic nuclei formed. We pass into the first second when the universe was a searing soup of fundamental particles. The temperature climbs past anything that matter as we know it could survive, and the equations, Einstein's equations of general relativity, the same equations that have guided us flawlessly all the way down, keep telling us the story, smaller and hotter, right up until the very last frame. And then at that final frame, the film tears. Because when you reach the instant we call the beginning, the mathematics does not give you a very small, very hot universe. It gives you something that is not a physical answer at all. It gives you zero size, infinite density, infinite temperature, infinite curvature of space and time. Every quantity that should be a number becomes infinite all at once. Physicists have a name for this. They call it a singularity. And a singularity is not a thing. It is not a place. It is the sound a theory makes when it breaks. Infinity in physics is almost never a real measurement of the world. When your equations start handing you infinities, they are not describing something infinite. They are telling you in the only language they have that they have stopped working. It is the mathematical equivalent of dividing by zero. Your calculator does not show you the true answer to 1/0. It shows you an error because the question itself has fallen outside what the arithmetic can handle. And that is exactly what general relativity does at the first moment of time. It throws an error. The theory that describes the expanding universe so beautifully, so precisely, cannot describe the one instant it is named after. Let me sit with you in the strangeness of that for a second, because it is easy to rush past. We have a theory of the origin of everything, and that theory cannot describe the origin. The map of the universe has a hole burned right through it, and the hole is located exactly where the story is supposed to start. Now, you might reasonably ask, is this just a quirk? Maybe if we had cleaner equations or made better assumptions, the singularity would smooth itself away. And this is where it gets worse, not better. In the 1960s, two physicists, Roger Penrose and Stephen Hawking, proved a series of theorems, mathematical proofs, showing that under general relativity and some very mild, very reasonable assumptions about how matter behaves, this singularity in the cosmic past is essentially unavoidable. It is not a mistake in the setup. It is not something you can dodge with a cleverer model. It is baked into the theory itself. If general relativity is correct all the way back, then the beginning must be a place where general relativity fails. The theory taken to its logical end proves its own breaking point. It is worth pausing on how unusual that is, because most theories do not politely announce their own limits. They just quietly give wrong answers and you have to catch them at it. General relativity does something rarer and in a way more honest. It tells you in its own mathematics precisely where it can no longer be trusted. It is like a map that instead of simply going blank at the edge of the known world has words printed at the border that read, "Beyond this line, this map is meaningless." That is a strange and almost noble thing for a theory to do. It hands you a warning along with its failure, and there is a subtlety here that is easy to miss. So let me make it explicit. The singularity is not necessarily a real physical thing that actually existed. Most physicists do not believe there truly was a moment of infinite density. Rather, the singularity is a sign that our description has run out, that the true physics of that moment is governed by rules we do not yet possess. Think of it like this. If you are navigating with a flat map of the Earth and you sail off the top edge, the map might tell you that you have reached a place of infinite strangeness, an impossible boundary. But there is no such boundary on the actual globe. You have simply reached the North Pole, a perfectly ordinary place where your particular flat map happens to break down. The infinity was in the map, not in the world. The singularity at the beginning of time may be exactly that kind of illusion, a place where our flat map of physics tears, while the real territory, whatever it is, remains smooth and lawful and simply beyond our current sight. The trouble is that we do not yet have the globe. We only have the torn map, and the tear sits precisely where the story is supposed to begin. So what is actually there at that first instant? The honest answer is that we do not know, and we cannot know, not with the physics we currently have. To describe that moment, we would need a theory that combines general relativity, which governs the very large, with quantum mechanics, which governs the very small. At the singularity, the entire universe is both unimaginably heavy and unimaginably tiny. So, both sets of rules apply at once. And right now we have no working theory of quantum gravity that can handle that. There are candidates. There are ideas where the singularity is replaced by a bounce, or by some finite gentle transition, instead of an infinite spike. But not one of them is confirmed. Every one of them is a sketch in the margins of a page we cannot yet read. Let me give you a taste of just how different those sketches are from one another, because it tells you how open this question really is. In one family of ideas called bouncing cosmologies, there was no true beginning at all. Instead, a previous universe collapsed inward, growing denser and hotter until just before it would have hit the singularity, some quantum effect halted the collapse and flung it back outward. What we call the Big Bang in that picture is really the Big Bounce, the rebound of an earlier cosmos, and time extends backward past it into a whole prior history. In another family of ideas, the beginning is a smooth, rounded thing with no sharp edge, the way the surface of a globe has no edge even though it is finite, so that asking what came before the beginning becomes as meaningless as asking what lies north of the North Pole. In still others, our universe is one bubble that formed in a vast, eternally inflating background, and its beginning was simply the moment that bubble nucleated with an endless landscape of other universes stretching away on every side. These are not idle daydreams, they are serious mathematical proposals by serious physicists. And the striking thing is that they cannot all be right, yet each is compatible with everything we currently observe. That is the honest situation. We have several radically different stories about the deepest question there is, the origin of everything, and no way yet to tell which one, if any, is true. And notice what that means about the phrase we keep returning to. It is not just that the Big Bang makes less sense the more we study it. It is that at the very deepest level, the level of the beginning itself, we do not even have one story we are trying to confirm. We have a shelf of competing stories and an empty space where the evidence should be. The beginning of the universe is not a solved problem with a few loose ends. It is an open frontier, as wide open now as it has ever been, and everything we build on top of it inherits that openness. And here is the human weight of it. When someone asks you what banged in the Big Bang, or what came before it, the deepest honest answer is that the theory does not contain that moment. The beginning, as the popular story tells it, is precisely the one place our best theory of the beginning goes dark. We have not lost the first frame of the film. It was never in the reel to begin with. So already before we have touched a single new discovery, before we have looked through a single modern telescope, the Big Bang has a hole at its very center, and we are only getting started because the next problem is not a hole in the theory. It is something that everyone thinks they understand about the Big Bang, and almost everyone has completely wrong. Part 3. The thing you were taught was wrong. There is a picture almost everyone carries in their head when they hear the words Big Bang. It is a picture of a tiny brilliant point sitting alone in a great empty darkness, and then suddenly, it detonates a cosmic explosion, throwing matter outward in all directions, filling up the empty space around it with stars and galaxies. It is a vivid picture, it is a dramatic picture, and it is wrong in almost every detail that matters. Let me take the pieces apart one at a time gently, because getting this right is the difference between understanding the rest of tonight and being quietly lost. First, the Big Bang was not an explosion in space. It was an expansion of space itself. This is a genuinely difficult idea. So let me give you the image physicists use. Imagine the surface of a balloon, and imagine you have drawn dots all over it with a marker. Each dot is a galaxy. Now you blow the balloon up. Every dot moves away from every other dot, not because the dots are traveling across the rubber, but because the rubber itself is stretching, carrying the dots along with it. There is no dot at the center of the expansion. There is no special dot from which all the others are fleeing. Every dot sees every other dot moving away. The expansion is happening everywhere all at once, to the fabric itself. That is what the universe is doing. Galaxies are not flying outward through space away from some central explosion. Space itself is stretching, and the galaxies are simply carried along on it like the dots on the balloon. And this is why the question people always ask, where did the Big Bang happen, has no answer. It did not happen at a point. It happened everywhere. The place where the Big Bang occurred is the place you are sitting right now, and also the most distant galaxy, and every point in between, all at once. There is no center, because there is no outside for a center to be measured against. Second, and this follows directly, there is no edge and no outside. The universe is not an expanding ball of galaxies sitting inside a larger empty room. As far as we can tell, there is no room. The expansion is not the universe growing into some pre-existing emptiness. It is the emptiness itself, the space itself that is growing. There is nothing for it to grow into. I know how strange that is to hold in your mind. Take your time with it. The stretching is not happening inside space. The stretching is happening to space. And third, here is the one that connects back to where we just were. The standard Big Bang theory does not actually describe the first instant at all. It describes the aftermath. It picks up the story a tiny fraction of a second after the beginning, when the universe is already hot and dense and expanding, and it follows the story forward from there, with breathtaking accuracy. But that mathematical instant of zero size and infinite density, the singularity we just spent so long inside, the theory does not reach it. So when we say the Big Bang, what the science actually describes is not a creation event. It is everything that happened after a beginning it cannot see. Now let me tell you where the name itself came from, because it is a small, almost comic piece of history that has been quietly misleading people for 70 years. In the middle of the 20th century, there was a real scientific fight about the origin of the universe. On one side were the people who thought the universe had a hot, dense beginning. On the other side was an astronomer named Fred High, a brilliant and stubborn man who believed the universe had always existed, roughly the same forever, with no beginning at all. High thought the idea of a sudden origin was faintly ridiculous, and in 1949, giving a talk on BBC Radio, he reached for a dismissive phrase to make the idea sound crude and silly. He called it with a sneer, "This Big Bang idea." He meant it as an insult. He was mocking it. And the name stuck. It stuck so well that today every child learns it, and every one of them pictures exactly the crude detonation that H. Oily was making fun of. The very picture that the theory says is wrong. The most famous name in cosmology was coined by the theory's biggest opponent as a put-down, and it has been shaping how the public imagines the universe ever since. There is a small irony worth savoring here. H. Oily was by any measure a great scientist. He did foundational work on how the elements heavier than helium are forged inside stars, work so important that it underlies much of modern astrophysics. He simply happened to be wrong about the beginning, and in his wrongness he handed the winning side its most enduring brand. The man who thought the universe never began gave us the name we use for its beginning. And the name he chose to belittle the idea has done more to spread a misunderstanding of it than any deliberate campaign ever could have, because those two little words, big and bang, plant the wrong image in the mind before a single fact can be explained. I dwell on this because language shapes intuition more than we admit, and a bad name is a kind of quiet, permanent misinformation. If the theory had been called, say, the Great Expansion or the Everywhere Stretching, generations of people would carry a truer picture in their heads. They would not ask where it happened because expansion does not happen at a place. They would not imagine an edge or an outside or debris flying through the dark. The whole tangle of misconceptions we just spent this part unknotting flows in large part from a phrase invented as a joke on the radio in 1949. So when we go looking in the rest of this video for the places where the Big Bang seems not to make sense, keep one thing in the back of your mind. Some of the not making sense was never in the universe at all. It was in the words we chose, but not all of it. Most of it, as you are about to see, is real, and it is written into the sky itself. I am telling you all of this for a reason that goes beyond trivia. When people say, as more and more of them do, that the Big Bang makes less and less sense the more we study it, you need to understand what part they are talking about and what part they are not. They are almost never talking about the core claim that the universe was once hot and dense and has been expanding. That claim is rock solid. It is not in danger. What is cracking, what is genuinely, deeply in trouble, is the precise version of the theory. The version that tries to nail down every number, every ingredient, every detail of how the universe grew from that hot, dense state into the one we see. That version keeps failing its own tests, and now that you know which part is bedrock and which part is trembling, we can go and look at the trembling, starting with a piece of the sky that agrees with itself for absolutely no reason at all. Part 4. The sky that agrees for no reason. I want to take you to the two most distant places you could ever look and show you something about them that should not be possible. Point a telescope at one edge of the observable universe. As far as light has had time to travel to us, more than 13 billion light-years away. Note what you see, the faint glow of the early universe, and measure its temperature. Now, turn your telescope around a full 180 degrees and look at the opposite edge of the observable universe, the same enormous distance away in the other direction. Measure its temperature too. The two temperatures are the same, Not roughly the same to about 1 part in 100,000. If you measured the warmth of those two utterly separate patches of sky on opposite sides of everything, you would find they agree down to the fifth decimal place. And now let me tell you why that is a genuine problem, one that kept cosmologists awake for decades. Those two regions of the sky have never been in contact ever, not once in the entire history of the universe. Light, the fastest thing there is, the thing that sets the absolute speed limit on any signal, any influence, any exchange of heat whatsoever, has never had time to travel from one of those regions to the other. They are, in the language of physics, outside each other's horizons. Each one sits beyond the farthest distance the other could ever have reached, even at the speed of light, even given all the time since the beginning. Think about what it takes for two things to have the same temperature. A hot cup of coffee and a cold room reach the same temperature because they are in contact, because heat flows between them until they settle into balance. Two regions of anything come to match because at some point they could talk to each other, could trade energy until they evened out. But these two patches of sky never could. They have never exchanged so much as a single photon. There is no mechanism in the standard picture by which they could have agreed on a temperature, and yet they agree everywhere in every direction to a staggering precision. The entire sky, all of it, patches that have never met, share the same temperature, as if they had all quietly conferred beforehand and settled on a number. This is called the horizon problem, and I want you to feel how deep it goes, because it is not a small technical footnote. It is asking why the universe is so uniform, so smooth, so agreed upon, when nothing in the theory allows for the conversation that would have produced that agreement. It is as if you walked into a stadium full of strangers who had never met, never communicated, never been in the same room, and found that every single one of them had independently chosen to wear exactly the same shade of a color mixed to 1 part in 100,000. You would not say, "What a coincidence." You would say, "Something is going on here that I do not understand. Something must have connected them that I cannot see." That is exactly the position cosmologists found themselves in. The uniformity of the universe is not a comfort. It is a puzzle. A smooth, even, agreed-upon cosmos is far harder to explain than a lumpy random one would have been, because smoothness implies communication, and the communication was impossible. Let me make the impossibility as concrete as I can, because it is the crux of the whole problem. Light sets the ultimate speed limit. Nothing, no signal, no ripple, no whisper of influence can travel faster than light. So the farthest any effect could have reached since the beginning of time is the distance light could have crossed in that time. That distance defines what we call a horizon, a bubble around every point, beyond which nothing could yet have touched it. And when we do the arithmetic for the early universe, we find that at the moment the microwave background was released, the horizon around any given patch of sky was tiny, far smaller than the sky we now see. The universe we observe today is stitched together from a huge number of these little patches, thousands of them, each one of which was at that early time completely sealed off from the others. No two distant patches had ever been inside each other's horizons. No heat had ever flowed between them. By every rule we know, they should have cooled to whatever random temperatures they happened to start with, and the sky should be a chaotic quilt of hot and cold regions, with no reason to match. Instead, it is smooth, uniform, agreed. And so, cosmologists were left holding a genuinely disturbing conclusion. Either an astronomical number of causally disconnected regions, all independently by pure chance, arrived at the identical temperature, which is absurd, or something happened in the very early universe that we were not accounting for. Something that let those regions communicate after all, or share a common origin before they were flung apart. The uniformity was not a detail to be filed away. It was a scream for new physics, and the flatness sitting beside it only made the scream louder. And there is a companion problem sitting right beside it just as strange, called the flatness problem. When we measure the overall geometry of the universe, whether space on the largest scales is curved like the surface of a sphere, or curved the other way like a saddle, or perfectly flat, we find that it is flat, extraordinarily almost perfectly flat. And that turns out to be its own kind of miracle, because flatness is unstable. If the early universe had been even slightly curved, that curvature would have grown enormously over billions of years, the way a tiny error at the start of a long journey lands you in a completely different country. For the universe to be as flat as we see it now, it must have started out flat to a precision of something like 1 part in 10 to the 62nd power. That is a 1 followed by 62 zeros. The early universe had to be balanced on a knife edge so fine that no one could explain why. So here we are. The universe is too smooth and too flat, and nothing in the basic Big Bang model tells us why it should be either. These are not small discrepancies. They are enormous glaring features of everything we see, and the theory on its own simply cannot account for them. Now, physicists did find a possible answer to both of these problems at once. It is a beautiful answer, an elegant answer, and it has become part of the standard story. But here is the twist that sets up everything to come. The answer they found is itself one of the strangest and most contested ideas in all of physics. In solving the mystery of the smooth, flat universe, they may have simply traded it for a deeper mystery, and that is where we go next. Part 5. The patch that became its own mystery. In the late 1970s and early 1980s, a young physicist named Alan Guth was wrestling with exactly the problems we just walked through. The smoothness, the flatness, and a third one involving certain exotic particles that the early universe should have produced in vast numbers, but which we never find. And he arrived at an idea so powerful that it solved all three in a single stroke. The idea is called inflation. Here is the picture. Inflation says that in the very first tiny fraction of a second of the universe's existence, far less than a billionth of a billionth of a billionth of a second, the universe underwent a burst of expansion so violent, so explosive, that it doubled in size and doubled again and again, dozens of times over, growing by a factor so large it is almost meaningless to write down. A patch of space, smaller than a single proton, was stretched in that unimaginably brief instant to something larger than the entire observable universe today. And watch how neatly this solves our problems. The smoothness. Before inflation, the whole observable universe was a tiny region, small enough that every part of it was in contact, could exchange heat, could settle into a common temperature. Then inflation took that already agreed-upon patch and blew it up to cosmic size, preserving its uniformity as it stretched. The two opposite edges of the sky match because before inflation, they were right next to each other, close enough to talk. Inflation just carried them enormously far apart while keeping the agreement they had already reached. The flatness. Take any curved surface and stretch it by a factor that large, and it becomes indistinguishable from flat. The same way the ground beneath your feet looks flat because the Earth is so much larger than you. Inflation flattens the universe simply by making it vast. And that third problem, the missing exotic particles. Certain theories predict that the hot early universe should have produced enormous numbers of heavy stable oddities called magnetic monopoles, and yet we have never found a single one. Inflation explains their absence effortlessly. If they were made before the Great Stretching, then that stretching diluted them so severely, spreading them across such an unimaginably large a volume that there would be at most a mere handful in the entire observable universe today. Far too few for us to ever stumble across. One idea, 3 deep problems solved at a stroke. You can see why it was irresistible. It is a gorgeous idea. It solves the horizon problem, the flatness problem, and the missing particle problem altogether. And it made further predictions about the tiny ripples in the early universe that later observations appeared to confirm. For these reasons, inflation became part of the standard model of cosmology, widely taught, widely accepted. On the surface, this looks like a triumph, a case where the theory faced a crisis and physics rose to meet it. But now, let me turn the idea over and show you its underside, because this is where the trouble lives. First, nobody knows what caused inflation. For this incredible burst of expansion to happen, there had to be something driving it. Some field, some form of energy, with very particular properties filling the early universe. Physicists gave it a name, the inflaton. But naming it is not the same as finding it. We have never detected this field. We do not know what it was, where it came from, or why it had exactly the properties needed to make inflation work. The mechanism that solves our mysteries is itself a complete mystery. Second, and this is stranger, In most versions of the theory, inflation does not cleanly stop. Once it begins, quantum effects keep it going, in some regions, even as it ends in others, so that inflation never fully switches off across the whole of reality. It keeps going forever, spawning pocket after pocket, bubble after bubble, each one a separate universe with potentially different properties. This is called eternal inflation, and it implies not one universe, but an endless, ever-multiplying multitude of them, a multiverse. Our entire cosmos, everything we can see, becomes just one bubble among infinitely many. The theory we invoke to explain our tidy, uniform universe ends up predicting an uncountable infinity of universes we can never observe. And third, the deepest cut of all, and it comes from inside the field itself. One of the original architects of inflation, Paul Steinhardt, a man who helped build the theory, became one of its most forceful critics. His argument is devastating in its simplicity. He points out that inflation in its full form is so flexible that it can be tuned to produce almost any outcome you like. Different versions, different starting conditions, different values of that mysterious field, and you can get a universe with almost any properties. But a theory that can predict anything, Steinhardt argues, predicts nothing. If every possible observation is compatible with some version of inflation, then no observation can ever test it, and a claim that cannot in principle be proven wrong sits uneasily at the edge of what we can even call science. So look at where we have arrived. To explain why the universe is smooth and flat, we invoked inflation. But inflation requires an undetected field we cannot identify. It may generate an infinity of unobservable universes, and one of its own creators argues it may not be falsifiable at all. We did not so much solve the mystery as relocate it and possibly deepen it. The patch has a hole of its own. I want to be fair to inflation, though, because it would be easy to leave you thinking it is nothing but hand-waving, and that is not true either. Inflation made at least one prediction that turned out to be spectacularly right, and it is worth knowing about. The theory said that the same violent stretching that smoothed and flattened the universe should also have taken the tiniest quantum flickers, the unavoidable microscopic jitter that quantum mechanics says fills all of space, and blown them up to cosmic size along with everything else. Those stretched out flickers would have become faint ripples in the density of the early universe. Slightly denser here, slightly thinner there, and those ripples would have left a specific calculable pattern in the microwave background and would have seeded the places where galaxies later formed. When we mapped the microwave sky in detail, the pattern was there, and it matched inflation's prediction remarkably well. So inflation is not just a convenient story, it has a real observational success on its record, and that is why so many cosmologists take it seriously despite its problems. But here is the maddening thing, the thing that keeps the whole subject honest. That same success can be produced by more than one version of inflation, and by some of its competitors too. The prediction that worked does not uniquely single out one theory, and so we are left in an uncomfortable middle place. Inflation is probably telling us something true about the early universe. Some real burst of expansion did likely occur, and yet we cannot say what drove it, cannot rule out that it spawns infinite universes, and cannot fully test the grandest versions of it. It is our best answer and an open wound at the same time. And that, more than any single fact, is the flavor of modern cosmology. Our best answers and our open wounds are more and more often the very same thing. And notice the pattern beginning to form here, because it is the real subject of tonight. Every time we push on the Big Bang, every time we try to nail down a detail, the theory answers, but the answer comes with a new question attached, often a stranger one than we started with. We are not running out of cracks. We are finding that behind each crack is another, and we have not yet reached the largest crack of all. The one that says almost everything in the universe is made of a substance nobody has ever seen. Part 6. The 95% nobody can name. Here is a sentence that should stop you cold, and I want to say it plainly before I soften it with any explanation. Everything you have ever seen, everything you have ever touched, every star in every photograph, every planet, every atom in your own body, all of it together adds up to about 5% of what the universe is made of. The other 95% is two things, and nobody on Earth knows what either of them is. Let me show you how we ended up making a claim that outrageous, because we did not arrive at it lightly. We were forced there, kicking by the evidence. It started with galaxies spinning too fast. In the 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford, was carefully measuring how fast stars orbit around the centers of their galaxies. And she found something that made no sense. The stars far out at the edges of a galaxy were moving just as fast as the stars nearer the center. That should be impossible. Think of the planets in our solar system. Mercury, close to the Sun, whips around quickly. Neptune, far out, crawls along slowly. The gravity holding them weakens with distance, so the outer ones move more gently. Galaxies should work the same way. The outer stars should lag, but they did not. They raced around at full speed as if held by far more gravity than the visible matter could possibly provide. It was as if every galaxy were embedded in a vast invisible halo of extra mass. Mass we could not see. Mass that gave off no light at all, but whose gravity was unmistakably there. An earlier astronomer, Fritz Zwicky, had glimpsed the same ghost back in the 1930s, studying whole clusters of galaxies, and finding they were moving far too fast to stay bound together by their visible mass alone. He had even given it a name, dark matter, and been largely ignored. Rubin's careful, patient work made it impossible to ignore any longer, and then the evidence multiplied. We found that dark matter bends light exactly as invisible mass should, warping the images of distant galaxies as their light passes through it, a phenomenon we can map directly across the sky. We found a place called the Bullet Cluster, where two galaxy clusters had collided and the invisible mass had sailed straight through, while the visible gas piled up behind, letting us see the dark matter and the ordinary matter physically separated from each other. And we found its fingerprints printed into the oldest light in the universe, the pattern of the cosmic microwave background, which only fits what we observe if there is roughly 5 times more dark matter than ordinary matter. 6 completely independent lines of evidence from galaxies to clusters to the infant universe, all pointing at the same conclusion. Dark matter is real, its gravity is beyond serious doubt, and we have absolutely no idea what it is. For decades, physicists have built exquisite detectors, buried them deep underground to shield them from noise, and waited for a single particle of dark matter to reveal itself. Nothing. Not one confirmed detection. We know it is there. We know how much of it there is. We know it makes up about 27% of the universe. And it remains completely, stubbornly anonymous. Think about how odd that situation is for a science. Imagine a detective who can prove beyond any doubt that a person was in a room. There are footprints in the carpet, a dent in the cushion where they sat, a warmth still lingering in the chair, a dozen independent traces of their presence. But the detective can never see them, never photograph them, never catch them, no matter how many cameras are set up, no matter how long the stakeout runs. For 50 years, the stakeout has continued deep underground with the most sensitive equipment ever built, and the suspect has never once shown their face. That is precisely where we stand with dark matter. Its presence is beyond dispute, and its identity is a total blank. Some physicists have even begun to wonder whether we are looking for the wrong kind of suspect entirely, whether dark matter is some exotic particle we have not imagined, or whether the whole framework of our search is somehow mistaken. That doubt, that willingness to question the search itself, is a quiet symptom of a field under strain. And I want to underline just how load-bearing this invisible stuff is, because it is not a minor character. Dark matter is the scaffolding of the entire cosmos. Without it, galaxies would never have formed in the time available. Its gravity is what pulled ordinary gas together into the first structures. What holds galaxies from flying apart? What shapes the vast cosmic web of filaments and voids along which all the visible matter is strung? Everything luminous in the universe. Every star and galaxy you have ever admired formed inside a scaffold of something we cannot see and cannot name. The bright universe is decoration hung on a dark frame, and that is only the 27%. The larger mystery, dark energy, is even further beyond our grasp, and it is the thing we turn to next. But dark matter is only the second largest mystery. The largest came in 1998, when astronomers measuring distant exploding stars discovered that the expansion of the universe is not slowing down. As everyone expected, gravity would eventually make it do. It is speeding up. Something is pushing the universe apart harder and harder, and whatever it is fills all of empty space and makes up about 68% of everything. We call it dark energy. In the Standard Model, it appears as that cosmological constant, the lambda in the theory's name, a fixed energy woven into the vacuum itself. It is the single largest ingredient in the entire universe, and it is the one we understand the least. The way we found it is worth telling because it is one of the great surprises in the history of science. In the 1990s, two competing teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone assumed it must be slowing. Gravity pulls things together, and the combined gravity of all the matter in the universe should be gently applying the brakes to the expansion. The way a ball thrown upward is slowed by the Earth's pull. The only real question, everyone thought, was whether the universe would eventually stop expanding and collapse back inward or coast outward forever at an ever-slowing pace. Nobody expected a third answer. To measure the slowdown, the teams tracked a special kind of exploding star, a Type 1a supernova, which always detonates with nearly the same true brightness, making it a reliable cosmic mile marker. By comparing how bright these explosions appeared to how bright they truly were, the astronomers could measure their distances, and by measuring their light, their speeds. And in 1998, both teams arrived independently, and to their own disbelief, at the same impossible result. The distant supernovae were fainter than they should have been. The expansion was not slowing down, it was speeding up. Something was pushing the universe apart, overwhelming the collective gravity of all the matter in it, and accelerating the growth of space itself. The discovery was so unexpected that the astronomers spent months hunting for errors before they believed it, and it eventually earned a Nobel Prize. But it left us with a universe whose dominant feature is a repulsive push we cannot explain, growing stronger in its effect as the cosmos expands and the matter thins out. Dark energy is not a quiet background detail. It is the thing that will ultimately determine the entire fate of the universe, driving the galaxies apart faster and faster until in the far future the sky itself goes dark. And it is the single most mysterious ingredient in the whole of physics. So let me put the whole recipe in front of you, and let me give you a moment to sit inside it. Picture the entire universe, drawn as a single circle, sliced up by what it contains. Almost all of that circle is dark. 68% of it, more than 2/3, is dark energy. A shade we cannot explain. Another 27% is dark matter. A second shade we cannot see. And then somewhere on that circle, you have to look closely to find it, is a thin, bright sliver, 5%. And that sliver is everything. Every star you have ever seen, every planet, every galaxy and every deep field image that ever took your breath away, every cloud of gas between the stars, every atom in your hands, in the chair beneath you, in the air you are breathing, in the body of every person you have ever loved. All of it, the entire visible cosmos, everything that anyone has ever looked at through any telescope in all of history, is that one small bright sliver, floating in an ocean of two things nobody can name. I want you to really feel that because it is easy to hear it as a fun fact and move on. And it is not a fun fact. It is one of the strangest situations science has ever found itself in. The overwhelming majority of reality is invisible to us and unexplained by us. And everything you have ever cared about, everything that has ever mattered to you, is made entirely of the 5% that the universe seems to treat as an afterthought, a rounding error, a thin, bright rind on the outside of a vast, dark thing. And here is the sharpest edge of it. This is the same theory, remember, that predicts the infant universe's temperature to better than 1 part in 1,000. That triumph is real, but it is a triumph that comes with a confession attached. To make the equations work, to match the sky so beautifully, the theory has to assume that almost everything in the universe is a placeholder. Two names, dark matter and dark energy, that are really just labels for two enormous holes in our knowledge.